Hi, this is Sylvia and welcome back to my videos. In this video, I would like to introduce you to HystereticSM, a new hysteretic material in OpenSees. New is in quotes because it's an extension of the current hysteretic uniaxial material in OpenSees. This material is available in the current version of OpenSees as well as OpenSeesPy. You can find the documentation for this material in the new OpenSees documentation pages. Just Google OpenSees documentation for GitHub, and there you will find the HystereticSM material. Going back to the basics of uniaxial materials in OpenSees, a uniaxial material defines a stress-strain curve, but it really just defines a y versus x relationship. So you can use it to define stress versus strain when you place it in a fiber. But if you place it in uniaxial sections, it really depends on the degree of freedom. It could be moment curvature, shear force versus strain. It could be axial force versus strain as well. Or if you put it in spring, same thing. You could look at moment rotation or force deformation. So it really depends where you put it, and all you're defining is this hysteretic response in a single degree of freedom in the two directions, positive and negative. Hysteretic material is the basis for HystereticSM, so I want to show you some highlights of that material itself. Here's the input from the manual. You input the envelope points. It could be bilinear, it could be trilinear, which actually can become quadrilinear. We define stress, strain for each point, and you have as many in the points in the positive direction as you have in the negative direction. Then you define this pinch X and pinch Y parameters. As you can see, they're shown here on the top right hand side, where they define the amount of pinching for your material response in the hysteretic loops. I will show you a little bit more about that. Then it's got the two damage parameters. One is for ductility and one is energy. And then it's got the unloading branch beta parameter. These are well defined and well documented in the OpenSees manual, but I'm going to show them one by one because they're also part of HystereticSM. One thing to note about the hysteretic material that you'll also see in HystereticSM is how you define the last point. So for the hysteretic material is the third point. And it can give you three different types of curves. So if you don't define S3 and epsilon 3, whether it's in the positive and negative direction, then you can get a simple bilinear response. So it's really nice. I use this a lot when I'm doing bilinear modeling. This is different from steel load 2 because this actually has stiffness degradation with cycling. So steel load 2 gives you full loops, while this is more of a Takeda type reloading cycle. So there's a little bit less energy dissipated, which I think is more representative of reinforced concrete structures, for example. So if you don't define S3, again, you get this bilinear response that is shown right here. On the other hand, if you define S3, it really depends on whether S3 is greater than S2 or if it's less than S2. So it's pretty much, is the stiffness going to change, but is it a positive stiffness or is it a negative stiffness? So if S3 is less than S2, then you have a positive stiffness. So these are the points S1, S2, and S3, and then this is going to be cyclically going to keep on going to infinity pretty much as a trilinear curve. If you define a negative stiffness, which means that S3 is less than S2, then when the stress reaches S3 and epsilon 3, then this goes on in a horizontal slope, okay? So that's what I mean by being a trilinear or a quadrilinear curves. So this is really handy because this does well with ASC 41 type of parameters early on. But now they're adding on more steps to this curve, so we need a few more points in the hysteretic material. And so that's one of the limitations, is it's only limited to 2 to 3 points, at the most 4 segments. It also has to have the same number of segments in the positive and negative direction, and it's limited to those. There's no envelope degradation, and also there's very basic recorder information. Interestingly, that's the case for all recorders, for all materials. But I've actually added some new recorders to this material, and hopefully maybe other materials may pick up similar recorders. So that's when I brought in HystereticSM to augment the hysteretic material so that I can address these limitations that were keeping me from being able to do the modeling I wanted to do. So this very first line at the top, you see the input that we have that you've already seen for hysteretic, all right? And then here's the input for HystereticSM. I brought in a lot more parameters, of course, because that's what happens when you bring in more options, but most of them are optional, and I've cleaned this up a little bit that it actually makes a lot more sense and it reduces the chances of error. Okay, and so what HystereticSM does is you can have, 7 points, therefore 8 segments to your curve. The number of points can be different in the positive and negative curves. So for example, you compare this positive from the negative, so you have a different number of points. The input, as I said, is better designed. It's less prone to error, which you have to do once you just reach a certain number of points, and as well as number of input parameters. I've introduced the envelope degradation, which is really cool and really important, because as much as Hysteretic has some damage parameters, it always reloads back to the same envelope. And as I said, I've added these recorders, and I'm still working on the recorders for this material. So I'm going to go through each one of these input parameters for this material one by one. First of all, the input. I've added this flag at the very top beginning called positive envelope, and then the optional negative envelope. Why is this optional? It's optional because if you leave out the negative envelope, I'm going to give you a symmetric curve in the other side. So here's an example here for a symmetric curve. Now this is all you have to input for HystereticSM. And heck, if you have less points, it's even that much faster of an input. Okay, and that's why now I bring in this flag of positive envelope and negative envelope. All right, and as you can see, you can have all the way to 7 input points in both directions, and they're separate and independent of each other. Okay, so you can have as many points up to 7 on either side of this envelope. So this is the first step, which is a lot cleaner. The pinching parameters that we had in Hysteretic haven't changed, so you still have pinch X and pinch Y. What I've changed is I've made them optional. Okay, pinch X is the pinching factor for strain or deformation during reloading, and then pinch Y is the same parameter for stress. Okay, I like them because they're simple. You don't have to define all these, fixed values, and all it really means is that if you have 1 and 1 for pinch X and pinch Y, then your extension, pretty much this line here, has a 1-to-1 ratio all the way through to the end. If you have pinching points that are less than 1, and they always have to be less than 1, then it's really about the relationship between pinch X and pinch Y along this curve. So let's say here's the two extremes. So we would start from this point here with the target over here. So that's 1-to-1. Now this point here, the hinge point, is going to be at, you go along 0.2 of that horizontal distance to the right, and then you go 0.8 up of the way. Okay, and this is something that you want to play with and parameterize. And so that is why you have these full loops, because you go less in the X and more in the Y. If you switch it and you use 0.8 and 0.2, so now you're going 0.8 here of the total length and 0.2 of the total vertical length, and that's why you get this pinching point right here. Okay, and so when you've got a lot of pinching, you want to use a larger number of X versus Y, and when you have more fuller loops, if you want to represent a steel cross section, then you would use parameters closer to 0.2 and 0.8, maybe play around with 0.3, 0.6, and things like that. Okay, but in this case, as I've pointed out, I've made them optional. The default is 1-1. So 1-1 means it's a straight line to the opposite point on the curve. Okay, so this is an improvement that I think is worthwhile, because so many times we have to remember to not forget the 1-1 at the end of our input. Here are some example curves that I've developed for the different cases. When you're looking at material behavior, you kind of want to make sure that you look at all the different loading cases. So on the top left, so in this case I have 1-1 right here, I've got 0.2 and 0.8, and here I've got 0.8, 0.2. And then I compare all of them here. So you could see the different shapes with respect to each other. Important to also see how does this act if it's only in compression or only in tension, to make sure that this is the kind of behavior that you are indeed looking for. Okay, so when you're testing material, make sure you do more than just symmetric loading. Okay, and here you see I'm using a material that's not symmetric between the two directions, just to make it that much more interesting. Okay, so these are the pinching parameters. Nothing's changed except for making them optional, and hopefully now you have a better understanding of them. The next set of parameters are the damage parameters. These I haven't changed either, okay? What the damage parameters do is they change the target displacement in the reloading cycle based on the basis of ductility and energy, okay? I didn't change them, but I've made them optional. So now they default to 0, 0. Before you actually had to define them for hysteretic, now they're default to 0. And here again is an example of this is damage 1 parameter on the top right and the damage 2 parameter on the bottom left. Now what you have to keep in mind is you still need to calibrate these. These are dependent on, it's difficult to normalize them when they're dependent both on displacement and force. And so when you're defining a material, you always need to compare it and evaluate it based on some test data that you have or some other model. Okay, so you build a material tester and evaluate what values for damage 1 and damage 2 apply to your case. Okay, in this case, when they're alone, they're going to be just like in hysteretic material. They do not change the envelope, and as you can see in these figures, they load right back onto the envelope. You can see that here. It loads right back to the envelope even at this point, and same thing here, it loads back to the envelope. Now, if you want to learn more about these materials, if you look at Michael Scott's blog, the one on the hysteretic damage parameters, then he explains, it's really cool, he explains what these damage parameters mean and how they're calculated. And as I showed you before, you know, this target displacement here in the reloading, well, this is the actual last maximum point. That would be where it's targeted to. What the damage parameters do is they shift the target maximum strain. And the shift is due to this factor D, which can be a function of ductility times this damage parameter 1, or energy, which is damage parameter 2. So go and have a look at this blog that explains what these different damage parameters do. He also talks about the beta that I will show you afterwards. So here's an exercise. It's difficult to separate you know, damage 1 and damage 2, they kind of have the same effect. Sometimes they're in different scales. It really depends on, because one is based on energy, which is both the force and the displacement, while the damage 1 is only on the displacement. So sometimes a value of 0.1 may be high for damage 1, but maybe not for damage 2. So you really have to play around. Sometimes you need values. I think here I'm looking at values of 0.01 and 0.1 for both cases, okay? And so that's what you see here, but that just happens to be the case for my loading. And it especially depends on how far you load. This I've loaded pretty far. The beta parameter is also unchanged, and it was already optional in hysteretic, so I haven't really done anything with it. What the beta parameter does, again, here it is from the Portwood Digital blog. He talks about how it's based on its mu, which is ductility to the power of beta, and that's the beta that you are dealing with right here, okay? So that defines the unloading stiffness as a function of the elastic stiffness. So if you set beta equal to 0, which is the default value, this exponent is 0, and therefore the unloading stiffness is the same as the elastic loading stiffness, which is always a good place to start, okay? And so here I show you the difference between beta equals 0 on the top right, beta is equal to 0.5, and then beta is equal to 1, and the significant drop in your unloading stiffness. Be careful with large values of beta because then you can actually bring in some instability and convergence issues into your model. So I typically go between leaving it at 0 and maybe using a value of 0.5. Here's an example of, you know, the full loading and unloading. A little bit difficult to see it here as separate, but then when you plot them all together, it's easy to see the difference in the unloading stiffness. Now we get into new stuff. So the very first thing I did is now the function itself, when you call the material, it returns values to you. This is something new. All other materials return a void array. I've put into HystereticSM to return values. And what the values are is it returns to you the input values that you've given, and actually all the values that it computes at the very beginning. It's kind of hard to play with significant figures, but I'll let you figure that out and you can round out the results. This is only done once when you define the material. Okay, so you can say, you know, input, this material input is returned by calling the material. Okay, so you can put that into a variable. I think this is really handy because now you know exactly what it's computing, as well as maybe you could put these into your post-processing or make your pre-processing that much easier. You can even just, if you don't care for the parameter, you can just put a print statement around the material definition. Okay, and so this gets returned once when you define the materials. I thought this was just a handy little feature, so Mike helped me to modify the code in OpenSees, the material itself, to return a value instead of a void. So I'm hoping other materials will do this. It's really helpful for debugging your model. Sometimes we send in variables, and so it's good to kind of figure out what were the variables that are interpreted by the material itself. The other thing that I've added is this envelope degradation factor. This envelope degradation factor works with your damage 1 and damage 2, okay, because it needs to know, wait a minute, what am I counting? So instead of do its own counting, I'm attaching it to those damage parameters that are already there. You can define a positive degradation value, and if you want a different one for the negative side of the envelope, if you don't define it, then it takes the same value as the positive. Now there's two things about it. If you have a positive value, then it will degrade both the strength and the strain. So it's going to go down like that in the curve. You see how I'm going down? This point here is moving over this way. If you have a negative value, it's only going to degrade strength. So this point is actually just going to go down in the curve. And I think my next figure is going to show you that. Okay. And so now we finally have degradation of the envelope, not just you know, the loading cycles, but also the overall response of your model. I thought this was important because some other materials do it, but I wanted to bring it into Hysteretic, which is such a nice and clean and robust material. So here's an example of, on the left-hand side, you have no envelope degradation based on using the damage 2 parameter, when you have no degradation, and then on the right-hand side when you have degradation. That's what I showed you before. This figure here is what I showed you earlier. Okay. Now, if you have bigger cycles, you see that we never quite go back to the envelope, and it's actually pretty clear here to see where the envelope is. You never quite recover what you had. Okay, and so this is important. Now, what I want to show you in the next slide is what happens if you have a positive value, which is what I was telling you before. Now the curve is degrading both in stress and in strain, so it's going in this way. Or if you have a negative value, then you only have degradation. You see this point here has only moved downwards, okay? And because this is associated maybe with damage parameter 1, that's going to be more and more as you go farther along. So even though this was a straight line in my envelope, that envelope itself is degrading to something like this, depending on the number of cycles, the ductility demand. So I think this is really cool because it's a lot more realistic to show some sort of, you know, fatigue and the effect of cyclic loading on your overall response. Also, what I've done is, it drives me crazy how the input for Hysteretic is in stress strain, so you have to define yx instead of xy. So if you want, you put this little flag at the very end, something like this, and that means that you're defining the stresses and strains in terms of strain, stress, by just telling it, hey, I'm using XY order, okay? By default is the YX order, okay? And so now you can see here's a strain, here's a stress, strain, and stress for my positive envelope. And you see how much cleaner your input is in this case? So I really try to do that for input just so that it makes debugging and even just writing your input stream a lot easier. Now another flag that I've put in is this print input. This is something that's done at the very beginning, just as it returns to you the values in a variable. Another option is to print output. It outputs all the input values. It doesn't output too much of anything that is computed internally, but it gives you a nice little printout of what your values are. This is something that is just easier to do rather than printing and trying to figure out what to do with what's returned to you. You just say print the output, and the first time it's defined, it gives you all the different values for this. So it's a good way of checking, but it's not very useful for pre and post processing. But I put it in there because I could, and I thought it was handy. Also, another new thing is these additional recorders that are just within the Hysteretic material. It'd be cool eventually to be able to put these into all the materials, but because different materials have different parameters, different points, different things, it's really hard to make a universal generalized material strain. So I've put these into the HystereticSM. Hopefully other material developers may copy the idea and do a similar type of output. Okay, now I've broken this up into groups. The first set is pretty much information about your deformations. These are depending on some limit states that you define as a user. I'm still working on this. And then this one here is a recorder that gives you all data. Okay, so I'm going to start from the bottom and then do the top, and then I'll show you just snippets of the concept of the limit state ones. Okay, so the very first command is all data. What this is going to give you, it gives you all the parameters, not just the input parameters, right? All these values here are input parameter, but it's also going to give you the maximum rotation, they call it in. So these are all the parameters that are used. So this is the current stress and current strain in the material. These are used. These are pretty much the internal parameters that are used for all the calculations that I do in the material. Okay, in case you're interested in these are really good for debugging, but this is a heck of a lot of data, especially when all this data you don't need. Okay, so if you want to get the current stress and strain, you just use the stress strain recorder. Okay, but this is something, again, helpful for debugging. Then this first set of recorders, I thought it was something easy, because oftentimes we don't want to know what is my strain, but what is my strain compared to the different points in my curve. And so that's what mu1 is. Mu1, for example, is just the ductility ratio. Okay, it gives you the current value of the strain divided by, if it's a positive, divided by the very first point. So this is what we want to call our yield point, right? So in the positive and the negative. And so it gives you the ductility right now at every point. So you could ask for mu1 or even just mu y, okay? This is only with respect to the very, very first point. In case you just want to normalize the strains, it's a lot easier for post-processing and visualizations without having to ask the material, hey, what is your yield strain? It does it for you internally because it's one of the internal variables. Then the second parameter wants to know is what is the plastic deformation, okay? Is the current strain minus the elastic strain, okay, which is defined by the stiffness, the elastic stiffness, okay? And so this is in positive and in negative, and so it just gives you at each time step what is the plastic rotation, which is the total rotation minus the elastic deformation. Then I've got these deformation demand to capacity ratios. These are 7-component arrays. It gives you the current strain divided by each one of these points. If you're in the positive, it divides it by the positive points. If you're in the negative side, it divides it by the negative points, okay? And so, for example, let's say I'm a strain point right here, okay? It's going to give you a vector of this strain divided by 1, 2, then 3, 4, 5, 6, and 7, okay? So in this case, these values are going to be greater than 1, and these values are going to be less than 1. So it kind of gives you where you are in your curve, okay? This is for the current strain, and then this is what is the maximum that you have hit. So these are good just ideas of where you are with respect to your points without looking at values of strains. So it's pretty much ductility, but compared to maybe your collapse limit state or your deformation limit state, or your yielding limit state, let's say. The last one is the limit state recorders, where you as a user actually define these stresses and strain values. that you want to compute your demand capacity ratios. Okay, so maybe these could be values that are somewhere along the curve here. And then the recorder is going to give you the ratios with respect to deformations or with respect to forces. Deformations makes a lot more sense, so it gives you the real time, the maximum absolute value. For force, it just gives you the limit state compared to just the real time, compared to whatever the forces are in all these different points. Okay, and then you can even ask for it, but it's easier to get those out of the input what the actual limit states are. Right now, this isn't working for some reason. When I ask for force limit states, it returns to you the deformation limit states. So give me some time to work through this and see how it goes. And that's it. That's all there is to this material. I wanted to kind of go through it to show you how easy it is to use and understand what the different parameters are so that you can have some fun with it.